All right, here's our video on 4.3, and getting into the swing of things here. I've got my page numbers. So, during our office hours, if you want to say, hey, I was a little confused when you were doing 4.3, page 2, you did this step. I'll be able to bring these notes out. For example, I just stapled the other ones from 4.2, and I could open it up and I could say right here, you could say, yeah, how did you go from here to here? So I think maybe we can figure out a system. And it'll also be helpful if you're sending me an email too. You can refer directly to the notes and also the time in the video. You could say, if you're sending me an email, you could say, at 17 minutes, you do the following on page 3. I can review that and kind of figure out a good response. So what 4.3 is, well, let's just jump into it. So suppose I have something like x double prime plus 4x prime plus 4x equals 0. So we just got done doing 4.2, or I just got done recording it, and so I'm in the flow of things. I would write down my operator. Looks like I can factor that. That's d plus 2, d plus 2. So here's something new. The factors are repeated. And so, I can go ahead and look at this first part and say, well, I know I'm going to get e to the minus 2t, but this would just give me another e to the minus 2t, but these are not linearly independent, so they can't form a basis. I know that this has a two-dimensional kernel because it's a second-order operator, but I don't have two linearly independent functions here. Question mark. So let's think through this and then figure something out. So e to the minus 2t is in the kernel. Remember, this symbol means an element of or belongs to. It's in the kernel of d plus 2. And it's also in the kernel of this larger operator. I need something else in this kernel. So I need another function in the kernel of d plus 2 squared that is linearly independent from e to the minus 2t. And so I'm going to try something that's really similar to this, though. And it's as similar as I can possibly get while still being linearly independent. Guess. T e to the minus 2t. So why is this as similar as it gets? Well, think about it. This is only one step removed from a constant. All constant multiples of this function are in the kernel. And what's a constant? Well, a constant is really, it's a t to the 0 kind of situation, right? T to the 0 is 1, so any multiple of t to the 0 is a constant. This is t to the 1. So if you think of it that way, I'm going from a constant to a linear function. So just a tad bit more complicated. Now, is this going to work? I don't know. Let's find out. Well, I do know, but the idea is let's try something. So d plus 2, t e to the minus 2t. Let's see what happens. So this is not in the kernel of d plus 2. So this first part is not going to be 0. Let's figure out what it is, though. So let's see, I have a derivative of this. That's product rule. So I'll have a 1 times e to the minus 2t, that's the derivative of t, times that stuff. Then I'm going to have a, let's do t minus 2 e to the minus 2t, there's that derivative. So that's the derivative of this function, are those two terms, plus 2 times that, plus 2t e to the minus 2t. Oh, well that's convenient. Look what happens. Those cancel. So what am I left with? I'm left with d plus 2 e to the minus 2t, and I know what this equals. It equals 0. How do I know that? Because e to the minus 2t is in the kernel of this operator. And you can check it, it equals 0. Great. So what that means is that our guess is in the kernel of d plus 2 squared. It's not in the kernel of d plus 2, but it's in the kernel of this larger operator. So now I have two things in my kernel, e to the minus 2t and t e to the minus 2t are in the kernel of d plus 2 squared. It's a second order differential operator. I have two linearly independent functions, and so then anything in the kernel, and by anything in the kernel I mean solutions to this homogeneous differential equation, anything in the kernel is a linear combination of those two basis elements. Okay. Don't worry, we'll do another one. And I'll give you a rule of thumb for dealing with these. All right? Okay. Page 2. Let's do another one. Let's see. There's an example. It's x1, 2, 3, 4 plus 6x1, 2, 3 equals 0. This is example 106 on page 149. So let's factor this, or let's write it out first. All right. Whoops, sorry, crooked. I can factor this a bit. This is d cubed, d plus 6x equals 0. Again, all the coefficients are constant, so it doesn't matter what order I'm writing this in. And this part is fine, right? I'm going to get an x equals e to the minus 6t. That's going to be in the basis of this thing, all right? So that's in the basis of kernel d4 plus 6d cubed, all right? Now what about this? Well, dx equals 0 yields x equals 1 as a possible solution. So 1 is in the kernel of d4 plus 6d3. But I have 3 d's here, and I only have 2 functions so far. These are linearly independent functions. Again, if you're having trouble with 1 as a function, it's a constant function. You plug in t, you get 1 no matter what. So I have 2 functions in my kernel. It's a fourth order differential operator, so there needs to be, the kernel is 4 dimensions. I need 2 more things. And I get them from here. So 1 is in the kernel of D. But what about the kernel of D squared and the kernel of D cubed? Now these might be a little easier for you to see. In hindsight, maybe I should have led with this. Well, what's in the kernel of D squared, right? Well, these are linear functions, right? Linear functions, a plus bt, right? The second derivative of any line is 0, right? Lines have no concavity. What's in the kernel of d cubed? Well, quadratics, right? Quadratics represent a constant acceleration motion. They have no jerk, if you will, no change in their acceleration. And so things in here are a plus bt plus c t squared. So what's in the kernel of d cubed? Well, 1 t and t squared form a basis of the kernel of d cubed. E to the minus 16 forms a basis of d plus 6's kernel. And so all together, this operator has a kernel with a basis of 1 t squared and e to the minus 6. So they're all linearly independent. Again, there's no way of adding and subtracting them to get any one of the others. So a basis for the kernel of d to the 4 plus 6d cubed is 1 t squared and e to the minus 6t. I'm sorry, I keep making it crooked. So then anything in the kernel, and again, anything in the kernel means solutions to this homogeneous differential equation. So then anything in the kernel is a linear combination of those basis elements. All right. I'm going to do a couple more examples. All right. Let's go to another page. All right, let's ignoring the whole factoring things because I don't want to make up an example. Suppose I had something like d minus 2 squared on x equals 0. All right. So suppose that was the factored form. And I'm not always going to have you factor these things. Sometimes I'm going to have you factor, but sometimes I'll just give it to you like this because I'm just interested in your ability to use the idea from the factored form. You might even want to pause the video at this point and see if you can't get a jump on this. So, if I were to write this out, here's what we can do, right? I can find part of the kernel, right? This is going to give me x equals e to the 2t. Because these are constant coefficients, I could have also have written this like this. And then this gives me something for my kernel as well. But that's only two linearly independent functions for a third order differential operator. I need another function, but I don't have anything different. So just kind of reviewing, right? This is in the kernel of d minus 2. 1 is in the kernel of d. They are also, so e to the 2t and 1, are also in the kernel of d minus 2 squared. But I need something else. I need another. And the problem is I have a repeated factor here. So that means I'm going to modify this function. So I would try, and I'm not even going to try, I would try this. It's going to work, right? Because it's very, very similar to the first example. So this would be my third basis element. So e to the 2t, t, e to the 2t, and 1. This would form a basis for this operator. So this is a basis. And so anything in the kernel would be just a linear combination of these functions. Let's do something a bit more involved, all right, just to really kind of push it. What about, so page 4, what if it has something like d plus 3 squared, and I had d minus 1 cubed, for example, on x equals 0. Okay. So what's going on here? Well, each of these factors is going to, for beginner, just to start with, going to give me some basis elements. D plus 3 gives me an e to the minus 3t. D minus 1 gives me an e to the t. But that's not enough. It's 5d. The kernel is 5d. I only have 2 things. We've dealt with a repetition. We know that, oh, well, I can just put a t in front of it, and that'll give me my second, right? So these two are in the kernel of d plus 3 squared. Those two elements will span that kernel. That's great. What about cubed? So this is in the kernel of d minus 1. It's a pretty good guess, you'd be correct, that this would be something that's in the kernel of d minus 1 squared. But what do I do next? I guess a bit of a pattern here, right? You might guess t squared, and that would be a good guess. And we'll try it to make sure it works. So let's try that out. If I have d minus 1 cubed, now I don't have to try out these, because I know this is going to be in the kernel down here, because think about what this means. This is d minus 1, d minus 1, d minus 1. So e to the t is also in this kernel, because the first factor gobbles that up. This is in the kernel because the first 2 factors gobbles up that function. The only thing we don't know is what happens to this. This is not in the kernel of d minus 1. It's not in the kernel of d minus 1 squared. Maybe it's in the kernel of the whole thing. Let's check. So this will be a little monotonous, but let's do it out. First, we'll do that bit. So product rule, 2t e to the t plus t squared e to the t minus t squared e to the t. Those two cancel. And the thing to watch for is what happened here. The result of operating stripped a power. Right? So the first d minus 1 brings it down to a t times e to the t. Oh, hey, look. Multiples of t e to the t are in the kernel of d minus 1 squared. So this is going to work out. This is going to equal 0. Done. All right. So just to generalize, if I had d minus 1 to the 4th, I would need a d cubed e to the t, because that would end up equaling some d minus 1 cubed on some multiple less. That 4th factor will whittle this thing down a power, putting it into the kernel. So that's repeated roots. Yeah, sorry. You're just slapping on an extra power of t as you increase in multiplicity. Oh, so what's the final solution of this whole thing? Well, it would be 5 things. So x is going to be a e to the minus 3t plus b t e to the minus 3t and more. This is from the d plus 3 squared plus c e to the t plus d t e to the t plus e t squared e to the t. And this part comes from the d minus 1 cubed. All right, so that's 4.3.